Today, one item on the agenda. So welcome to the new people. Niels is going to be showing us off some work that he's been doing to illustrate training using GPUs on Flyte. And so with that, I will turn it over to Niels.
Thanks, George. Hi, everyone. I'm Niels, and I'm a machine learning engineer in the Union AI team. So today I wanted to talk about using Flyte to train Pytorch models on GPUs. So before I get started, just want to make sure people can see this full screen right here. Excellent. Also, feel free to ask questions or interrupt if anything comes up. So I'll talk about training parallelized GPU accelerated Pytorch models on Flyte. This is the Flyte OSS sync, September 21, 2021. The asterisk here is that this is for single node training. So this is not multi-node training. So we're going to be training some models on machines with multiple GPUs. In the future, we're going to support multi-node training. That involves a little bit more work. I think there's an MPI operator pretty much done and in the works. So let's get started. The outline for this workshop is I just wanted to motivate this, like why scale up and accelerate your training in the first place. Besides just like having it train faster, which is then the obvious motivation, but I did want to go a little bit into the model development lifecycle, and then from there go into general ideas about scaling models, and then kind of going into a deeper dive into Pytorch parallelism, the main concepts there, and then give you a little demo of such a task and workflow in Flyte that uses Pytorch and GPUs. Finally, some takeaways for you and next steps. So let's get into it. So in this context, I'm referring to model development lifecycle in a kind of a narrow scope. So I mean the process of training a model in the lab, setting aside dataset collection, labeling and annotation, and then also ignoring for now the production deployment. And also like the maintenance involved with retraining and stuff like that. So really here, I'm assuming that you have a fairly high quality data set. So for example, in the supervised setting, you have a pretty good, you're pretty confident that your labels appropriately capture the concepts you're trying to model. And so this is really about the R&D kind of iteration process before even determining that your model is good enough to deploy. So the question, one of the questions here is like, how do you get there? And so just to review the bias variance trade-off, you can think of bias as how close a model's predictions are to the ground truth. So if you have some training set, really how good are the predictions? And so in a regression setting, you're trying to predict some real valued, continuous variable. In the graphs below, this is kind of a cartoon that's often depicted when people try to explain the bias and variance. So on the left side, you can see an underfit model. So you have on the x-axis the variable you're using to predict the output variable, which is on the y-axis. And you can see, you can kind of eyeball a little kind of curve there where as the predictor increases in value, there's a correlated increase in the output, but then after a point, it kind of drops off. So if you just draw like a straight line to try to fit this curve, you can see, also, can you see my cursor? Just want to make sure. Okay, excellent. So I can use this. You can see like the difference if you sum up or if you average all the distances, like it's not a great fit. So that's a high bias model. On the right, all the way on the right, you can see you've just done a connect dots type of model. So maybe you've introduced, high degree polynomial terms in your model, and now your model is just tracing through all the dots in your training data. So this is a low bias model and that it fits the training data perfectly, but it's a high variance model, which is a bad thing. And variance is, there's a lot of ways to look at it, but one way to explain it is it's how stable a model's predictions are in the face of perturbations in the training data. So imagine if I add a little dot up here, this model, you can imagine this dotted line is gonna change like crazy. Or if I add another dot training point over here, again, the model is gonna change like crazy. Whereas if I add a dot here, with a very simple model, just a straight line, that line is not going to change that much. It's just sort of kind of stay fairly stable. And so it's robust to random noise or perturbations in the data. And obviously in the middle is like this Goldilocks model where it kind of fits the data pretty well, but it's not like if I introduce a data point up here, you can imagine it's not going to change that much. So another way people like to think about this is in terms of this plot where the x-axis is some kind of model complexity. So you can think of this also as like how long you've been training like deep neural net or any model of interest. But in this case, model complexity can mean how many terms, how many features are in your training data, how many interaction terms you're introducing to the data, things like that. Now the y-axis is error. And generally speaking, this is obviously an idealized plot, but generally speaking, the more complex your model is, the more capacity it has to fit the training data. But then you're also trading off variance in that if it's really complex, it can just kind of memorize the training data. And then once you have something out of distribution in deployment, it's not going to know what to do. So like the predictions for those data points that are out of the training set distribution will throw the model off. And so as you increase model complexity, you're better and better fitting the training data, but then you're also likely going to overfit the training data. And so I'll show you one more plot to kind of hammer this home. So in the real world, this is what error curves, loss curves generally look like. So this is probably a batch-wise plot. Actually, no, these are epochs. Never mind. So I just took this from Stack Overflow. In blue is the training set loss. So the lower, the better. And the test set loss is in orange. And so you can see after around epoch 100, just as a reminder, epoch is like how many times you've gone through your entire data set. So around epoch 100, you're kind of seeing this sweet spot go away, and the gap between the blue and the orange line you can see as a measure of overfitting. So here in practice, we assess overfitting by splitting our data into training set and test set. The model doesn't see the test set ever to make predictions and to update itself. You iteratively update the model, and then you plot the different losses. Okay, so I hope that gives you some intuition, some sense of the kind of science behind machine learning. It's very much empirical. You have to look at the data, you have to look at the model. There are kind of general rules of thumb of how to debug models in this way. But yeah, in my experience, loss curves don't typically look like this. They're a lot more bumpy, and especially if you have very complex problems and things you're trying to model. Okay, so with that, I'll get into the model development lifecycle, sort of as I see it. This is not canonical in any way, but so it's good to start small. Small model, small data. So you say you have 1 million data points, and then again, I'll preface this with the context that we're using a model family that's, well, actually, this actually sort of applies to various other model families, but here, since we're using Pytorch, let's say you're using deep learning or neural nets and all the bag of tricks that come with modern neural nets. So say you have like a non-trivial problem, a kind of benchmark data set, and you have like some proprietary data in your company and you're trying to model it. You don't know, there's no literature on any of it. You might like look for some papers that sort of fit the problem. So, okay, I have some kind of architecture, say I'm using like coordinates or something, or transformers. So first I want to see if I can actually overfit on just a small subset of data, like 20 data points or 10 data points. And that makes sure that the model implementation is correct. You know, even with tools like Pytorch, you don't have to code backprop by hand anymore, which is awesome. But still, gradients might not be flowing through all the parameters of your model. You want to, make sure of that. So there are a few other debugging steps here that I'm kind of glossing over or skipping. But the main question is, can I just overfit? Can I just memorize it, the data? So if no, then there's something wrong with your implementation. There's a bunch of things you can try here that I won't go through, but there's something wrong with the model implementation if you have to go back. If yes, then you can go to phase 2. And if you can answer yes to this question, you kind of, these are relative terms, very hand wavy, but you go to a medium model and a full data set. So then now the question you're asking is, can my model fit the training set, like all of my available training data without overfitting on the test set? So even if you're using like a smaller medium model, and if you're overfitting, then try a smaller model, or try regularization or something that kind of bounds or constrains the complexity of the model in some way. And if you're seeing like, test loss and training loss just keep going down, and you've been training for thousands of epochs, or maybe even less, but if you see this pattern where test loss just keeps going down, then you can go to phase 3, which is, a large model. And here a large model can be something that generally won't fit on your laptop, like a modern laptop. So you're no longer, you're like struggling. Maybe you're like, each batch is a batch size of 1 or 2, and it's just taking forever. And just so now so you're kind of well justified. Your test and training loss is going down. And now you're fairly confident that scaling up your model size is going to get you more performance. This is what this workshop is about. Here in the teal. So there are other ways of thinking about this. So you don't necessarily need a large model. Maybe you're trying to tune hyperparameters on a fairly simple model that trains fairly quickly, but the hyperparameter space is huge. And as a reminder, hyperparameters are non-learnable parameters. So these are things like, what is the architecture? What is the learning rate? So these are things that are not tunable by whatever the learning algorithm is that you're using. So I'll kind of, this is a topic for another workshop, perhaps. For now, I'm just going to talk about, scaling up your model and the things that are associated with that. So these are maybe I should have clicked through these, but yes. So in bold is what the focus of this workshop is. Cool. So we start small as like an ant and then become a mountain. Oh, well, this is not working. Let me refresh. Ah, okay. So there are two types of parallelism, there are probably more, but two big buckets are data parallelism and model parallelism. So in data parallelism, what you do is you have some canonical model, you replicate it across your devices. In this case, we have 4 GPUs. So we just copy over the weights across all the GPUs, and now we can handle larger batch sizes. So say you've scaled up your model, and you can only process, a batch size of 10 or 10 per device. So now you can throw more devices at the problem. It's not, in a sense, it's wasteful because you're copying model weights over, but then, what can you do? So instead of batch size of 10, we have an effective batch size of 40. And this, again, glosses over a lot of details, but so each device handles the batch and computes gradients for the model, and then whatever framework you're using will generally handle the combining of those gradients in order to update your original, like the canonical model. So if you think of this as one update, then this updated model is then all the weights are propagated across all the devices for the next round. With model parallelism, it's tougher because it's sort of, you kind of have to get into the guts of your model. And what you're doing here is a single model can't even fit in a single device. So this is when you'd want to use model parallelism. You can obviously combine the two, which then increases the complexity of your code. But here, what you're doing is you're distributing the weights across different devices. You're handling whatever batch size you can handle. And it's kind of passing the tensor from the data batch through to all the different devices. You get the gradients in the end, and then you update your model. So these are the two type of frameworks for parallelizing a model or your training algorithm. And so getting into Pytorch parallelism, I'll only get into data parallelism for now. It's a little easier to think about and demonstrate, although I think it would be worth another talk or workshop to show model parallelism. So here's the general anatomy of a Pytorch training script. I tried to do it in 10 steps, but alas, could not. So it's 11 steps. So first you want to define a model here, then load your data, initialize the model, specify some kind of optimizer, so SGD or Atom or whatever else. And then for some number of epochs, iterate through your data, compute the loss, backpropagate the errors, do the gradient update, and then collect metrics. Here I'm kind of glossing over the test set stuff, but you can imagine it looks very much like this without the backprop. And then you save your model at the end. And this is the artifact that you're interested in persisting and maybe deploying. So there are two ways of doing data parallelism in Pytorch. The first is this torch.nn.dataparallel. It's quite magical in that it's a one-liner. So if we have 4 GPUs, we just wrap our model inside the data parallel class. I just did this to be explicit. You don't even have to do this. It'll automatically just use all of the available devices in the runtime environment. But in this case, I'm just specifying, device ID, GPU 0, 1, 2, 3. And then pretty much everything else in your code is the same, except for when you save it, you have to access this .module attribute in data parallel. So that's amazing. What's happening roughly under the hood is that data parallel splits the batch across specified GPUs, performs the forward pass on each GPU, concatenates the outputs, And then the gradients from each device are summed into the original module. This is all happening under the hood, and it's great because you don't really have to think about it. With the other type of data parallelism in Pytorch, you have to do a little bit more. So I'd want to say that this is all you have to do, but there's more with using distributed data parallel. Basically, you need to spawn the n number of processes for each GPU from rank 0 to n-1. Then you need to invoke this init process group function before running your training routine. And then you have to write code carefully, being aware that rank 0 is the host process. So there are things you generally want to do in the host process that you don't want to do in the other processes. So I'll just kind of breeze through these. So you have to spawn some number of processes using this multiprocessing.spawn function. And here I'm specifying this trainer, which is the training routine. That it's a function that encapsulates all of the model. So what's trainer? Trainer is a function that does basically all the stuff I showed in the anatomy of a Pytorch script, except you have to, there's like a little ceremony you have to do before you start training, which is you set these environment variables and call the init process group function with some various other settings. Then you define your distributed data parallel class which wraps the model. And then you pretty much do all the same stuff. So there are some gotchas, obviously. So when writing code carefully here for using this type of data parallelism, things that you want to think about is you kind of want to, sometimes you want process-specific metrics like GPU utilization, but generally, if you're just reporting loss and accuracy and other kind of model level metrics, you want to do it in the main process. So here I'm logging the training loss and making sure that the rank is 0, which is the host process. And also the same thing with saving the model weights. Okay, so it looks like I have maybe 20 minutes left. So to summarize the kind of conceptual stuff, data parallel is great because it's a one-liner change, but there is a performance overhead because under the hood it uses multi-threading. So it's subject to the Python global interpreter lock, which I won't get into, but safe to say that the kind of the better way would be to use distributed data parallel, because even though it has some additional setup code, it uses multiprocessing in the background, so each GPU has its own process, which implies better performance. So some things to think about when you're training a distributed Pytorch model is, on the modeling side, if you're using dropout, that implies that you have like this binary mask over your weights, and so that's going to consume more memory. So one thing to think about. The precision, the float precision of your model will also consume more or less memory. And when you're performing like custom operations only on the host process, you need to invoke distributed.barrier to block all the other processes from continuing execution. On the data side, if you're downloading data locally, so if it's like some flat file you're downloading, do that first in rank 0 to avoid race conditions. And you'll, for almost every setting, you'll have to think about what batch size fits into memory. So generally, I sort of do this empirically, but you can, of course, do back of the envelope calculations to get yourself in the right ballpark. And then, as I said, metrics, like unless you're collecting process-specific metrics, you want to check that you're in rank 0 before you collect them. Okay, Sweet. So I'm going to demo really quickly the Flyte snacks example. So this is all the stuff I'll show now is on Flyte snacks for you to try out and read. So it's the classic MNIST data set. It looks like this, digits, handwritten digits from 0 to 9. And we'll be using a convnet to take the pixel images and then predict the digit. So before I show any code, I did want to, okay, cool. I did want to just run like a quick experiment. So I'm just going to kick off on the single node, single GPU Flyte workflow. I am going to just test out different batch sizes. So I'm going to run this job for, let's say, just 5 epochs on a batch size of 64. And I'll run 3 of these just to show you at the end what generally you kind of want to look for when you're kind of profiling your model training runs. I'm going to double this to 128. Make sure we're doing 5 epochs. And then just one more for good measure. 5 epochs. Batch size of 6. Oh, no, let me do even more. So 512. So while these run, let me show the code that does this. Actually, it might be better to just go to the documentation. So again, as I said, this is in the tutorial section of the Flyte documentation. It goes through with exposition and code at the same time, all the steps you need to implement this. So I won't go through step by step. But the big parts are, as I said, in the anatomy of a Pytorch script, you're defining the model here. This is just Pytorch code. You're defining the data loader. So Pytorch comes with a pre-built MNIST loading function. And this kind of might look familiar. This is the training function for iterating through batches of your training data. You're updating the model here. And then you're collecting metrics down here. And what this looks like, since we're using weights and biases, I guess a quick plug on the weights and biases. Don't know if it's technically an integration, but you can use it with Flyte very easily. So that would be worth another talk perhaps. But so Nobleglade 62 is the thing we just started running. These are some model metrics. So as the epochs go from 1 to 5, I think this job is wrapping up soon. You can see the training loss here per batch. It goes down. Yay. So this is the bias decreasing, speaking in terms that I introduced early in the workshop. And then we also see that the test loss is decreasing. So this is a good sign. And accuracy, you can think of as the opposite of loss. It's like how well your model is doing. And then here, under the system metrics, you can see certain metrics that weights and biases is collecting about GPU, CPU utilization. So we're not using as much memory as we can for this particular machine. I don't know which instance type this is or what the specs are, but and also utilization is fairly low. So this is, we're not, this tells me that we're not using like the best use of this of the resources allocated to this Flyte workflow. So this is the experiment that I ran with the 3 workflows is probably going to run in sequence since I'm not sure how many GPUs we have available. Let's just look back here. Cool. So these are the 3 ones. I'm not sure. I wonder if these are it. Oh, yeah. Okay. So if you squint, I guess as we increased batch size, memory allocated, and GPU utilization. Yeah, I don't know. I haven't looked at these data, but this is kind of like the exercise you go through when you're experimenting with different models, trying different batch sizes, trying different model sizes. I would love a tool that would help me think about this in a more systematic way. And then finally, just to wrap up here on this demo side, this is the multi-GPU training example. You can see here that we're just importing a bunch of the stuff from the single GPU example. So we're reusing the model definition, we're using our hyperparameter definition, and certain other functions for logging. The main difference, as I showed you with the extra ceremony you have to do with this, is this distribution, this setup function. So this initializes this process group that helps Pytorch coordinate all the different, batching and gradient updates across all the different processes. And then you might notice here that I'm only doing the weights and biases setup and logging and all that on the main process. There are some other things here that, if anyone's curious, we can chat about it maybe offline. But this is pretty much it. When you define your task here, you just have to make sure, we did a little bit of extra stuff here for distinguishing between sandbox and then like an actual like backend. But really all you have to do is specify, your GPU, number of GPUs you want, memory and storage, all the regular things. And yeah, I think we wanted to do maybe another talk on like how to configure your backend to support GPUs, but conditioned on that, you should be off to the races training models with Flyte on GPUs. Let me hop back onto the slides just to summarize some stuff. So main takeaways is to start small to ensure your model is implemented correctly. You can characterize the convergence and overfitting dynamics in this small data set and small model that you can do iterate locally. Scaling up reduces iteration time. So iteration time for getting insights onto your analysis or insights about your model. And then before scaling up, know why you're scaling up. So, you don't want to prematurely do that. Next steps would be multi-node training with the MPI operator, and then improving cost effectiveness with interruptible instances. And before I end, we just also wanted to announce a new thing we're trying, which is lightning talks. So these are very short, kind of 5-minute talks that you don't even need to prepare a slide deck for. It's like if you just have an idea about Flyte or excited about a new package that you found that has some like relevance to what we're doing within the Flyte team, Flyte ecosystem, we would very much encourage people to go check out this forum. It's just a Google form. You can either give a talk or propose a talk idea if you don't want to give a talk. And I'll be making a point to like push the Flyte team to give lightning talks. I'll also be probably giving these since they're very lightweight and they're designed to be lightweight and you don't have to like you can literally do these last minute if you want. And with that, thanks for your attention. And I'll give it back to you, George.
Thanks, Niels. That was awesome.
Yeah.
Stuff. Keithan, do you have anything you want to add before we?
I have a couple of things that Niels showed, and part of the lightning talks that people should propose and probably do. So we do have a distributed training example for SageMaker. If you're using SageMaker, the real difference that you need to understand when you're doing distributed training is that from Flyte's point of view, it's running one unit of work. So it has to have one output being returned. And that's what, Niels was just showing, that if you are process 0 within your MPI-COM world, you say that this is the guy who's the leader who's output all the outputs. Flyte supports that too. You can do that in the code as well. So what Niels showed is like a fully just using the basic Flyte constructs to construct a deep learning job. We could go beyond this, like basically, if you're using data loaders or something, you could write a transformer for it and get the data loaders directly loading from an input data that's passed. We haven't done that. So, if anybody is interested in contributing that code, that will be amazing. But for the distributed training case, we do support something called as ignore output. So if you're non-process 0, if you just raise an error called as ignore outputs, then Flyte will assume that it's okay for you to have not produced outputs. And then it correctly shows up in the UI. So definitely try out the SageMaker example as well. And then, as Niels said, we are working on a better example with MPI and Horoward. And even you could use Glue or so to do distributed training. That should be coming soon. But yeah, we would love to hear any thoughts and ideas and suggestions on this front.
I just wanted to ask, I think someone
Can you increase your volume a little bit, Soren?
Oh, sorry, better now?
Yes.
Sorry. I just wanted to ask about hyperparameter tuning, and I've seen that Stephen basically asked the same question in the chat, I guess. So yeah, so what's your recommendation to actually combine that with Flyte or such a training job? Do you already have some experience?
Yeah, I guess that's the motivation behind the whole Flyte-Kit-Learn RFC, to make that easier. But in theory, you could do the search, within a task. I'd have to think a little bit about how that would work with distributed data parallel. If you're like tuning these, multiple very large models, which I've never done in practice because it'll take a week to like train one model in my experience. So yeah, you kind of have to do some other, you have to be like kind of satisfied with a single model if you're training like fine tuning like a BERT model or something like that. But if you're using, I would say if you're using just vanilla Pytorch, yeah, you could, I'm not familiar with Optuna, but with the other tuning libraries that I'm familiar with, like they really just handle like the search over random settings or, distributions and things like that. So in theory, you could do that within a task, Flyte task. The whole thing with Flyte-Kit-Learn is that it's a layer that then kind of orchestrates this at the workflow level. So yeah, you specify a grid, it pre-samples the grid or the distributions, and then spins up a bunch of map tasks with your training code. So that's the convenience there, which I'm excited to help build out.
Yeah, that's cool. I was just thinking when you showed when you started the different runs with different parameters manually, I thought, okay, if we can now automate this in a workflow, perfect. Yeah, cool.
Yeah, I like to say that. So people did that, for example, at Lyft, but they did it manually. We did not have a specific API layer for it. And then I think there was one smaller API layer for single node. So again, what Niels showed is one node. From Flyte's point of view, that's one task. You can do whatever you feel like. It has 8 GPUs. I think on AWS, there's one node that has like 16 GPUs or something. It's pretty much for most base 90% of the applications, I would say, unless you start writing a completely new model from scratch, and that takes for a while. But that being said, so again, I'm not plugging SageMaker. I don't want to, but SageMaker does have a hyperparameter tuning thing, and we've kind of added that just to showcase how the expressiveness of such a system could look like, and then Flyte-Learn essentially takes that to being native in Flyte. And this is nothing to do with the backend potentially. It's purely how we can write this and expressively and also get right metrics from the system, because quite a bit of it is visibility, right? If you don't have visibility, I don't think it would be that useful. So yeah, I'm excited. I was like really excited to see the RFC, and would love to work with any of you guys who would love to collaborate on that. Yeah, Stephen, where's your MLflow example that you had, right?
It's in progress at the moment. We're deploying Flyte, so then we'll have the integration once we have Flyte running.
Awesome.
I guess oh, sorry, go ahead.
I was just going to ask for any other questions. Go
Yeah,
ahead.
I should say there's a lot of gray areas in between. So you could make training more efficient. Like say you're using BERT, you could have a thin layer on top that's learnable and then freeze the weights of BERT so that you're not collecting gradients on this gigantic model underneath what you care about. So I can imagine in that setting, you could do hyperparameter tuning on just the architecture of that thin layer on top. So yeah, it's like Lego bricks. That's how I see deep learning these days.
Yeah.
If there are no more questions, thanks very much, Niels. That was enlightening. And we will see everybody in a couple of weeks. So Sandra will have this up on video later today sometime if you want to pass it on to your colleagues. And we will try to integrate it with the docs. That's our newest trick. All right.
It's already documented, George. So
no, integrate the video with the docs. That's our new trick.
Awesome.
All right. Thanks, everybody.
Thanks, everyone.
Thanks.